Deep beneath California, inside a machine cooled to temperatures approaching absolute zero, scientists are trying to protect something incredibly fragile, a quantum state. The reason is simple but astonishing. In the quantum world, particles do not always behave like the objects we see around us. They can exist in multiple possible states at once. But when the surrounding environment interacts with them, that delicate quantum behavior can quickly disappear. This is one of the central challenges of quantum computing. At the heart of a quantum computer are tiny units called qubits. A traditional computer bit has a definite value, 0 or 1. A qubit is different. Through a property called superposition, it can represent a combination of possible states until a measurement is made. When multiple qubits become entangled, their states can become deeply connected. This gives quantum computers a way to process certain mathematical problems using principles that have no direct equivalent in ordinary computers. But there is a major obstacle. Quantum states are extremely sensitive. Heat, vibrations, electromagnetic interference, stray particles, and even tiny interactions with the surrounding environment can disturb them. This is why many quantum computers operate at temperatures incredibly close to absolute zero. Scientists are essentially creating a tiny protected environment where quantum information can survive long enough to be manipulated. And that leads to one of the strangest questions in modern physics. What happens to a quantum possibility before it becomes a definite result? The mystery goes back decades before quantum computers existed. Consider the famous double-slit experiment. When particles pass through two openings without information revealing which path they took, they can produce an interference pattern characteristic of waves. But when the experiment is arranged so that information about the path becomes available, that interference behavior disappears. The important point is that quantum mechanics treats information as something extremely significant. This strange behavior is part of the larger measurement problem. Quantum theory is extraordinarily successful at predicting experimental results, yet physicists still debate what the mathematical description actually represents. Does a quantum system truly remain in several possibilities until measurement? Is the wave function simply a mathematical tool? Does every possible outcome continue in a different branch of reality? Or is there another explanation that future physics has not discovered? Different interpretations provide different answers, while often producing the same experimental predictions. That is what makes quantum mechanics so fascinating. Even Albert Einstein was uncomfortable with the idea that quantum mechanics might describe reality as fundamentally probabilistic. He believed there could be deeper information beneath the theory, hidden variables that would restore a more familiar picture of nature. Then came physicist John Bell. Bell transformed this philosophical disagreement into an experimental question. His famous inequalities showed that certain kinds of hidden variable theories could make predictions different from quantum mechanics. Experiments testing these predictions repeatedly found results consistent with quantum theory. Entangled particles displayed correlations that could not be explained by simple classical ideas about independently existing properties. The lesson was profound. At the smallest scales, nature does not behave according to the rules our everyday experience teaches us to expect. And now quantum computers are turning those strange principles into engineered technology. Google's Willow quantum processor became an important milestone in this development. The processor contains 105 qubits and demonstrated progress in quantum error correction, an essential requirement for building larger and more reliable quantum machines. One of the most important ideas demonstrated by systems like Willow is that increasing the scale of a quantum system does not necessarily have to make it uncontrollably fragile. Better error correction can help preserve useful quantum information. Willow also attracted enormous attention because of a specialized computational benchmark that it completed extremely quickly compared with the estimated time required by a classical supercomputer. However, this result needs an important clarification. It does not mean quantum computers are already faster than classical computers at everything. They are not. Quantum computers are designed for particular categories of problems, and many practical applications are still being researched. The real importance lies in proving that increasingly sophisticated quantum operations can be controlled and protected. That brings us back to the deeper mystery. If a quantum computer performs calculations using superposition and entanglement, what exactly is happening inside the system while the calculation takes place? Physics gives us equations that predict the results. The machines demonstrate that those predictions can be used. But the underlying interpretation remains debated. And the mystery becomes even more interesting when we realize that quantum behavior is not limited to laboratories. Everything around us is ultimately made from quantum systems. Atoms, molecules, light, and the matter inside our own bodies all obey quantum laws. There is another layer to the quantum mystery that becomes even more fascinating when we stop thinking about computers and start thinking about the universe itself. Quantum mechanics does not simply describe tiny objects moving through space. It describes a world where probability is built into the mathematical structure of nature. At first, this sounds like ordinary uncertainty. If you roll a die, you might not know what number will appear, but the die already has a definite physical state. Quantum uncertainty appears to be different. Before a measurement, a quantum system can be described by a combination of possible outcomes. The theory does not merely say that we lack information. It gives us a mathematical description in which several possibilities can coexist. That distinction has kept physicists debating for generations. And it becomes especially important when quantum systems grow more complicated. Imagine a group of qubits interacting with each other. Their combined quantum state can represent an enormous number of possible configurations. This is one reason quantum computers are potentially powerful. But it also creates a huge engineering challenge. The more components you add, the more opportunities there are for unwanted interactions with the outside world. A single microscopic disturbance can introduce an error. Another disturbance can introduce another error. Eventually, the information that made the quantum computation useful can be lost. This is why quantum error correction is so important. Instead of relying on one fragile physical qubit, researchers can distribute quantum information across many physical qubits in a carefully designed way. The goal is to create a more reliable logical qubit that can survive individual errors. It sounds almost contradictory. To protect a quantum computer, you may need many more qubits than the number you actually want to use for computation. But that overhead is part of the path toward large-scale quantum machines. The challenge is not simply building more qubits. It is building qubits that can work together while maintaining extremely low error rates. That is where recent advances become important. Researchers are gradually learning how to control increasingly complicated quantum systems. Yet even if engineers eventually build enormous fault-tolerant quantum computers, one mystery will remain. The machine will still be operating according to quantum mechanics. And quantum mechanics will still leave us asking what its mathematical description actually means. One interpretation suggests that the wave function physically collapses when a measurement occurs. Another interpretation says there is no special collapse at all. Instead, different outcomes become associated with different branches of reality. Other interpretations attempt to preserve a more definite picture of physical properties while adding additional structure to the theory. The fascinating part is that experiments have not yet settled this philosophical question. The mathematics can remain the same while the interpretation changes. That means a quantum computer could become incredibly powerful without telling us which interpretation of reality is correct. And perhaps that is an important lesson. Technology does not always answer philosophical questions directly. Sometimes it makes those questions sharper. Quantum computers are doing exactly that. They force us to manipulate superposition rather than simply discuss it. They require engineers to preserve entanglement instead of merely describing it. They make decoherence something that must be measured, controlled, and reduced. The mysterious principles of quantum physics are becoming engineering requirements. And that changes the relationship between humans and the quantum world. For decades, quantum mechanics was mostly something scientists tested with carefully designed experiments. Now researchers are attempting to build machines whose operation depends on maintaining those strange effects for useful periods of time. That is a major conceptual shift. We are no longer simply observing the quantum world. We are learning how to engineer it. But engineering something does not necessarily mean understanding its deepest meaning. Humanity can manipulate gravity without fully explaining its ultimate nature. We can use electromagnetism without answering every philosophical question about fields. And we can build quantum computers while still debating what quantum states represent. Perhaps that is normal in science. Understanding often arrives in layers. First comes observation. Then mathematics. Then technology. And sometimes, much later, a deeper explanation. Quantum computing may currently be somewhere between the mathematical and technological stages of that journey. The equations are incredibly successful. The experiments continue to confirm their predictions. And the machines are becoming more sophisticated. But the interpretation remains open. That uncertainty is not a weakness. It is an invitation. Every unexplained question creates another reason to investigate. And quantum physics has plenty of them. Why does measurement produce definite outcomes? Why does entanglement produce such powerful correlations? What exactly is the wave function? Is it a physical object or a description of information? Could spacetime itself emerge from quantum information? These questions connect quantum computing to some of the deepest problems in modern physics.